Good morning. Can everybody hear me?
Yep.
Lovely. Is it okay to start?
Yes, please.
Yes, smashing. Good morning, everybody. Thank you very much for attendance. My name is Rob Redmond. I'm the UK Sales Manager for Power for Vertiv. And can I just add, it's a pleasure to be here today. And thank you very much for allowing Vertiv to pop along to your session this morning and discuss power and topology at the 2021 AUE. So thank you very much for that. I think the last time we presented with the AUE must have been 6 or 7 years ago. We presented in person, so it is very nice to be back. I have some colleagues with me today that will present shortly, but just for the first 5 minutes, if I may, I thought I'd take the opportunity just to introduce you tentatively to Vertiv as an organisation. So Vertiv, let's just have a look at what we have here on our slides. So the agenda, as we say, introduction to Vertiv in a second, at which point afterwards my colleagues, Mr. Bully and Joe, will pop online to discuss fundamentals of UPS and specifications, technology, the topology of systems and resilience. And we will also take a bit of time to talk to you about cooling applications and cooling considerations. So Vertiv as a company, we bring together a tremendous amount of hardware and software. We manufacture very large AC power and DC power applications, and we provide solutions and services coupled with software for applications within edge and IT systems, rack and PDUs. We've typically focused tremendously in the data center arena. We design systems, we manufacture all of our own products, and we have solutions available that reduce costs. We have a world-class service, and we have a tremendous team that sits behind us that supports applications for deployment within enterprise, co-location, hyperscale, and edge type technology. We're also incredibly involved in 5G. We work tremendously in turnkey solutions for applications within telco applications, should we say. I apologise, the signal here isn't fantastic. If we look at it as a presence, we're a relatively large company. It's safe to say we turn over just over £4 billion. And within the business, directly employed, we have 21,000 employees. So if we look at us from a global perspective, we certainly do have a reach. Europe and Middle East, which is where we concentrate today for our discussions. The manufacturing facilities that we have across Europe are extensive. We have manufacturing facilities all over Italy and wider. We have a tremendous amount of service field engineers and technical support available to you as a business. The service centres are around about 300 of them that we have globally. Now, you may recognise a couple of the brands. People will recognise Chloride, I'm quite sure, from the early 90s in terms of power, whether that is traditional power products for UPS and light industrial applications. Liebert is another brand of Vertiv's, so you'll recognise Liebert from a cooling perspective. Netsure, I'm sure, from DC applications. If one was looking for DCIM and connectivity, we have the Trellis package, Canoa racks, which we produce in Germany, and of course we also have Geist as a flagship brand for PDUs and power monitoring down to BIOS level. So it's a huge breadth of applications, and as I say, everything that we see on the screen are physically manufactured by Vertiv. These are not badge products at all. We have a tremendous opportunity and reach in terms of product capability. We're not new to the universities community, albeit a little bit conservative. We don't wave a flag that often, but I can safely say we've been heavily involved with the university community within the UK. Some of the sites are listed on screen for you today. In the Q&A session later, if anybody would like to discuss any application of the existing infrastructure or deployment or future projects, please feel free to call me. But as you can see there, we have installed megawatts of power and thermal capacity across the university sites within the UK, and a shining example there being Astro House, Southampton Data Centre, University Data Centre on the right hand side, with which from memory we installed about 1.4 megawatts of UPS power capacity within that particular environment. As I say, when we talk about the solutions that the business can provide to the community, it is extensive. So if you have applications or requirements that are power related or thermal management related or IT systems for edge and infrastructure, coupled with the ability to service, maintain and monitor with the service packages within the business, we have a very, very broad reach, I think it's safe to say. So I think the takeaway here is we manufacture all of these products. We have a voice. If you want to speak to us technically, please do so. We're very interested to understand your thoughts and your views in terms of topology. We're very much interested in understanding what's coming over the hill, because we have an obligation to support and protect products and applications, and we design our systems to future-proof against new designs within technology. So on that note, what I'd like to do is introduce you to the following people that you're going to see on the screen. Russ Bully, Senior Application Engineer, Chartered Engineer, been within the business for a tremendous amount of time. Russ is going to talk in a moment moving forward, and halfway through the presentation, Mr. Bully will introduce Joe Thomas, again, Chartered Engineer, Mechanical. So Russ is very, very much a power man, and Joe will take over halfway through regarding mechanical applications. So on that note, can I just say thank you very much for the audience, the attendance. It's very nice to be here. And at that point, Mr. Bully, could I hand over to your good self?
Russell, you're on mute.
About that, the label was over the microphone button, which wasn't very helpful. Anyway, yeah, just so that we can see where we are, where UPSs and batteries and sit within a conventional architecture. Obviously, we've got medium or high voltage coming into a campus through a transformer, then some switchgear, where we probably join up with a generator. Then we go to a UPS with a DC system for energy storage, and then critical loads downstream. So specifying UPS is really one of the challenges in the university space, because there are some hybrids out there, and there are some hybrids that are being developed at the moment, and it may not be a conventional UPS that you're looking for, especially if it's for a research application. But the fundamental questions remain the same. How resilient does the system need to be? By resilience, we mean how are we going to ensure that we can take the UPS off the servicing? And what does it mean if we have to maintain a battery, for instance? A lot of clients nowadays don't want generators, and that could mean that we have to look at hybrid battery systems. What are the UPS ambient conditions? The UPS doesn't need the same ambient conditions as the generator in modern designs, so they can be in two separate places to save money. What will the maintenance system be? If we're dealing with a campus in Malaysia or Borneo or whatever, what sort of maintenance would you require? And in particular, whether you're going to need a watch system. We have a system where we have a 24/7 coverage available on UPSs and generators, etc. They're just some of the questions that we need to consider. There are two basic types of a static UPS. We've got monolithic and modular, and there are benefits and pros and cons for each. So modular tends to be a unit with a buzz bar system inside. So the red dotted line shows the UPS, and those modular UPSs can be slotted in and out to suit load conditions. So you might have a load on one part of a campus that is going down. So you could take the modules out of that UPS, walk them across the campus into another building and plug them into an identical UPS and increase the capacity in another place, for instance. That's also available on a modular battery basis as well. So these systems tend to be where the industry is at the moment, and the modular UPS, if you pay a little bit more money, those modules can be removed and inserted hot. So you don't need to turn off the UPS to do servicing. You don't need to turn the UPS off to change a module, provided you follow the right instructions, etc. So that's a picture of what a modular system would look like. Each one of those black boxes is part of the module. But on the traditional side, the monolithic side, then it is possible to have independent UPSs side by side, arranged so that one UPS could be taken out for a service, another UPS could fail, and all of the load would go on to the third UPS. So resilience is a big part of specifying and planning applications. And there's a traditional monolithic UPS. So the factors that we need to consider when we're specifying UPS systems is obviously what is the load and how important is it. You know, can we have 5 minutes a year for servicing, or is 30 minutes or an hour okay for servicing a year where the UPS is going to be off? What's the electrical circuit should be used for the system? Do we have neutral available, for example? If it's going into a foreign application, we might have a strange electrical system that we need to connect into. What action is required if the unit needs to be serviced? In other words, do we want the local staff to react, or do we want the system to go off to the vendor to tell the vendor that the UPS needs something doing? Do we want the ability to expand and contract? Is there a site generator? How fast will it take the load? And obviously that will influence the battery autonomy required. And then maybe the specification of power events on the site, yet again, thinking about the third world, maybe we need to put lithium-ion batteries in to have more cycles and quicker charging, and that's obviously a different battery type to normal, and that means how quickly is the recharge of the batteries required. What's the fault current? It's something that keeps coming up over and over again. The fault current that can be handled by a UPS is also a factor that you need to think about. It tends that the cheaper UPSs probably don't have the copper work in the back of the UPSs for large fault currents, and obviously you've got to tailor the fault current to suit the UPS. So supply type we've mentioned. Do we need a generator? Resilience? Are there any load harmonics? Power factor is something we've got to think about. UPS losses. Cheaper UPSs tend to have bigger losses. Do we need to put a neutral in? That's the bottom diagram on the right hand side, so that the transformer preserves the neutral, and we've got a 3-phase without a neutral supply into the UPS. And we've got to engineer the UPS to be able to energize the transformer, obviously, to get it up and running. So I just wanted to say a little bit about centralized power systems. We have a lot of confusion in the industry between UPS and centralized power systems. If a life safety system is to be used, then we have a different BSEN that we use for those systems. And what it means is that if we're talking about fire lifts, emergency escapes, smoke ventilation, control systems on fire alarm systems, voice over Ethernet systems for alarms, then really we should be specifying a 50171 system. And the essential difference, and there's a lot of differences, but the essential difference is that the inverter within the 50171 needs to be able to clear the fault within 5 seconds and then recover within 5 seconds of clearing that device on battery alone. So the idea is that there's a mains failure, there's a fire in the building, part of the electrical infrastructure gets a short circuit, the system should be able to clear that short circuit and then recover and put the circuit back on again, all on battery operation. So it's quite a specialized device. I just ask people that if you are specifying a UPS and it is a life safety, or it could be graded as a life safety system, maybe by a court, then really think about 50171 systems. So we are also looking at new things that are going on within the industry. And one of the things that is being implemented nowadays, especially on larger UPSs, is the ability for the UPS to test itself without using an external load bank. And the idea is that by using grid technology, which we're going to talk about in a while, we can actually throttle the input to the rectifier in a UPS and actually use the battery to send circulating current round the bypass, back into campus and back again, in order to prove the UPS and the battery. And Vertif, we call this a safe capacity test. So the idea is that we don't need to rent a load bank. Really we're using the building, the load on the UPS, and topping that up by throttling the rectifier. And in so doing, we are testing not only the UPS and battery, but the infrastructure within the room, the cooling system, etc., etc. So that's a new thing that is coming along, and obviously it uses the same cable and switch gear that you've already got connected. Obviously, it goes without saying that if there's a power failure while this happens, then we always maintain the output load, and the UPS will always look after the output load using the batteries. So another thing that is going on is using fuel cells instead of or in parallel with a battery within the UPS. Obviously, people are wanting to get rid of generators. Generators are being seen as a dirty alternative. Although I have to say that the fuel industry is coming to the challenge, and it looks like we're going to have 100% biodiesel available for generators in the future. The problem with that is they've got a short shelf life of diesel, so you actually need to use the diesel or rotate the diesel. And I don't think, and I stand to be corrected, that polishing the diesel is always the answer to 100% biodiesel. So diesel is seen as something that we should be considering getting rid of. And the idea is that we use a fuel cell in place of the battery system. So if we look at this bottom left hand diagram, there's our UPS with the utility power coming in, and on the bottom left hand side you can see there's a fuel cell, and then on the right hand side there's a lithium ion battery. The idea is that the fuel cell takes a few seconds to get going. So if there's a power failure, then the lithium ion battery will step in to provide the current for the load. Once the fuel cell gets up to full power, then we back off the lithium ion battery and the fuel cell carries on providing the power out. Obviously, where we've got different loads on a UPS system, this is the middle diagram, there is the possibility of having different load structures and different fuel cells, and therefore different characteristics that we need to operate within to get the fuel cells and batteries to work together with the output loads. So there's a lot of work going on at the moment about adopting that. One of the things that we have to remember is that the fuel cell is unidirectional, not bidirectional as per the lithium ion battery. So it's important that while that goes on, the lithium ion battery is recharged maybe from the fuel cell if there's no mains available, so that it can actually take the UPS function should the fuel cell fall over because the gas runs out or there's some other problem with the fuel supply to the fuel cell. It might be just worth reminding everybody that there are fuel cells out there that can produce hot water. So using this as part of a heating system is entirely feasible. Balancing the two, the electrical and the mechanical load on the fuel cell, might be a challenge, but that is available if you felt that was something that you were interested in. And then the right-hand diagram is actually using the fuel cell to backfeed the grid and to keep the UPS alive. So we've got the mechanical loads being fed directly from the fuel cell because there's a short break, so we can turn the mechanical loads off and then put the mechanical loads back on again once the fuel cell is up and running. But at the same time, the IT load is running on the lithium ion battery until yet again it gets the feed from the fuel cell. So I think you can understand that there's quite a lot of interest in that and work going on at this moment in time. And I understand that Vertiv have got a test rig if you guys are interested in seeing that. So hot off the block, I don't know whether you've been monitoring what's been going on the national grid this week. Yesterday, on the wholesale market, I think it was yesterday or the day before, the price hit £7,000 a megawatt hour. And today they're firing up West Burton coal-fired power station because they're worried about the pricing on the national grid. So this slide was written a couple of weeks ago. It could well be there's going to be some lucrative money to be made using batteries in the future to inject power either back into the grid or to use battery power on campus when the price goes high. And I had somebody speaking to me yesterday. Apparently, Octopus were paying £35 a megawatt hour on Wednesday afternoon to those who had got power to inject into the grid. So we've gone from a place where it wasn't really of interest to somewhere that actually could be of real interest. And just to recap why this is happening, we've got errors in the system. That's the bottom paragraph in the slide. National Grid do have errors in the system, and this is one of their slides, and I've put a link on there to their document on it, where if they don't forecast the energy tomorrow correctly, they order the electricity today. When they get tomorrow, if there's a difference between the two, then they have to use reserves, and those reserves can be from a lot of different sources. The other problem that we've got is what happened in 2019 with the Little Barford power station trip. If you look, and I'm not going to go through every particular slide on this, if you look, we started off at 1652 with a circuit fault. Within 10 milliseconds, the frequency had dropped down to 46.2, which was 49.6, which was a fundamental, real shock to the system. And then it went down again to 49.2 in that second peak at the bottom at 14:53:19. Now, what this is telling us is that if this sort of event happens, the National Grid want to pay people to really quickly come back on the system, which is what happened on the right-hand side of the graph, to actually get the grid back up to 50 hertz. And they will pay good money for that. So it could well be that you guys are going to have some good storage facilities to be able to use those to earn money. The other thing that is happening is that we've got high energy costs happening at different times of the day in different parts of the country. And yet again, sorry to quote Octopus, but you can buy energy off night from Octopus at 5p, and I understand EDF are 4p overnight. Store it in a battery, that's the red area on that diagram, and then release that energy at the peak periods during the day. So this basically means that we're using the UPS to cut off the load and to run on batteries until the batteries go down to a predetermined point and then come back online. Obviously, without a gap, without dropping the load, without any load problems. And of course, if it's really lucrative to sell the energy in the battery, then maybe inject that back in the grid and get paid for it. So all these things are happening, and my gut feeling is that it's going to get more interesting as we get more and more electric vehicles on charge. So this is a slide, I'm not going to go through all of it, that we've got cost savings and revenue potentials that are available in the system that you could actually use your existing equipment for to actually get benefit for the university or campus. The big thing for us as a UPS manufacturer is to decide what the minimum state of charge of the battery should be. And we do that in conjunction with you. Obviously, you can oversize a battery. You could buy more battery, but that's a big capital cost. You really want to have maybe 30, 40, 50% left in the battery for critical loads. And that will depend on whether you've got a generator or not. And these preset times, preset stages in the battery state of charge are something that need to be programmed into the system in conjunction with your normal routines and your attitude to risk at the end of the day. But we're happy to do that, and if you're interested, then give us a call and we'll see where we could go from there. Our system is basically a standard UPS with a control system, with a battery storage system, and then the critical loads downstream, but the ability to export and keep the critical loads supplied at the same time. And it's quite a clever algorithm that manages this. And if you're you've got a UPS that's a modern UPS, then it could be possible to do this with several vendors in the industry as well as Vertiv. The other thing that's going on is really a debate about how the grid is going to be formed as we go forward. And I'm aware that a number of universities have their own grid system within a campus. And we're talking to a couple of universities about that at this moment in time. But there are some considerations that you need to think about with regard to battery applications. And indeed, there are some storage applications that are coming online that could be of interest that don't involve batteries. We've got a couple of mechanical applications which are showing potential, let's put it that way, at this moment in time. So keeping Vertiv on its toes, we are available to advise on cycling and efficiencies and cost savings that could be made, etc., etc. So when we're talking about optimizing power supplies, especially within the critical space, it's really important to realize that there are some techniques that we can use to be able to actually minimize the risk to an installation, but in so doing there may be costs applied. So it's a balance between risk and capital at the end of the day. So we have a system called the tier structure. In fact, there are 3 systems. There's a European standard for resilience. There's also a German standard for resilience as well. But they all follow roughly the same sort of criteria. So here we've got a UPS with a dual power supply coming into it. We have an external bypass and we have an output onto a switchboard, which is the SWB. And then downstream, we've got a circuit board. And then below that, we've got a distribution board with a critical load on. And it could well be that if we're talking about IT space or server space, that dual load has that load has a dual input. So that means it's got an A and a B input, hopefully from different UPSs and different sources. So what we're trying to do, we're trying to analyze this circuit to avoid single points of failure. And indeed, this technique can be used on mechanical systems as well, on cooling water systems, etc., etc. So what we're trying to do is avoid a place that could shut the whole load down with a single point of failure. So we've got lots of different subsystems within a system, and sustainability or maintenance factors account for something like 70% of infrastructure failures. So tier 1 is what we've just been looking at, is a single power path without redundancy, providing the availability, and that gives us a 99.671% availability. Tier 2 is a single power path with redundancy, giving us 99.741, and tier 3 is giving us redundancy with concurrent maintainability, and that now gives us 99.9% availability. And then tier 4 gives us redundancy, fault tolerance, and concurrent maintainability, and that gives us 99.99, and that's where 4 nines comes from. You've probably heard 4 nines being offered by people as a way of designing a system. But what does that really mean in practice? So just remember that these ratings are limited by the rating of the weakest subsystem that will impact on the load. So this could be mechanical, electrical, it could even be the security system. So what does it mean? So it means that if you're 99.99, you have 5 minutes a year, or 0.43 hours every 5 years of the service being off. If we're talking about the tier 1, maybe we're talking about 1,729 minutes per year off, or 144 hours over 5 years. So it depends on what your client is looking for to which system that you need to design to. This is a table that basically highlights the different tiers, and you can see that compartmentalation and current maintainability of fault tolerance really are the things that define the tier level. Compartmentalization means not having cables running the same routes, basically, not having systems in the same place, just to clarify. So tier 1, this could be a boiler, a fan, a chiller, but it's a UPS in this diagram. This is tier 1, single module, but it's got a maintenance bypass. Tier 2, we've got 2 systems in parallel. Each of them is not loaded above 50%, so that if one needs to be taken out for servicing, the other one can pick up the whole load, vice versa, and then we've got the maintenance bypass over the top. But if you note on the output, we've got a common switchboard, so we've still got a single point of failure in that switchboard where it says system outputs. Tier 3, now we've got dual systems supplied by 2 power supplies coming in. So the bottom UPS is supplied by supply B, the top UPS is supplied by supply A. The buzz coupler between the output board of UPS A is not coupled to UPS B, but could be if we need to maintain the switchboard. And then downstream, we have an A and a B feed to each static switch, which could be in the server or it could be in the rack. And then we've got the server load being shown as load 1 or load 2. So a static switch is a system for doing very fast transfers between 2 incoming power supplies, and they range in all sorts of sizes, right up to 5,000 amps. So that is the way of generating quite a good system, but this is not fault tolerant. So if we had a major fault on this system, we might still lose the load. So there we go to tier 4, and in tier 4 we've got dual supply UPSs on each side for A and B. We've still got the same maintainability downstream, but now this system is fault tolerant because it's in different places. We've got diverse routes going to the loads, and the A system and the B system do not go above 50%, because obviously if B fell over, A has to pick up the total load. So it's quite a comprehensive system. It's a different way of looking at the design of electrical systems, and in particular it's a way of talking to clients about the things that are of interest to them. Quickly going to talk about energy and carbon saving, we've just talked about the portfolio through what Rob was talking about. Got lots of different devices available, And obviously, the newer the device, the more technology we've got built into that device to be able to save energy and to work intelligently. So lots of things are available to do that. And we've got different aspects within the IT space to be able to look after the heat that's being given off by the IT equipment, and in particular, we've got the integrated cabinets that are fully equipped for electrical and mechanical systems. So they've got batteries, UPSs, PDUs, cooling units, all built into one cabinet, bespoke to your application, and they get bigger. The third picture, the aisle picture, shows a system that is sitting in a room. The one on the left of that, the cabinet, is a standalone device where it's all encompassed in the design. The aisle design is using the room as a plenum in the conventional way. And then on the right hand side, we've got a set of freestanding enclosures for data centers that could sit outside a campus, etc. So all of those things are available, and the idea is that the implementation of those goes hand in hand off-site. So you can actually project manage it, assemble it, test it off-site, bring it on-site, put it in position. You know exactly what you're getting. You know how it's going to perform because you've tested it off-site in a Vertiv factory, and then you bring it on-site, put the wires on it, switch it on, and off you go. And that saves the problem of constructing on site and commissioning on site, and that is also carried on with our prefabricated buildings. These are made and assembled in Croatia. And it's a very popular solution that if you've got a space problem, all you've got to do is put a concrete plinth down, and you can order a pre-engineered or a bespoke solution going forward. And yet again, all designed and constructed off-site, proven off-site, tested off-site, signed off off-site, bought on-site, assembled, put the wires in, switch it on, off you go. And of course, full maintenance package and hand holding from Vertiv UK as you go forward. So we've got a poll question at this point here. And I think I have to stop sharing and go to the poll questions. I might need some help here. So if you could look at the poll question, and I see that we've got some people who have already voted. The polls are in the tabs next to the chat box and people box on the main screen. And if you could vote in there, be very interested in whether you are interested in an optimization assessment, which is free of charge from Vertiv, to come in and look at your infrastructure and tell you how to improve your energy efficiency. And that's part and parcel of the service that we do within Vertiv. If you've got any questions on that, or you're interested in going forward on that, then we're very happy to talk to you about that. And it looks like there are a few people who are interested. So it's all part and parcel of the service that we've always done at Vertiv, and we even did it at Chloride. So if you're interested in that, or you think it's a development that you'd like to have a discussion about, then give us a chat. And with that, yeah, we've got about half and half at the moment. Be interested to see how that develops. With that, I'm going to pass over to my colleague Joe Thomas, who's going to continue the presentation from a mechanical point of view, and I'll be here at the end for questions if you've got any.
Joe, just so you know, you are on mute. Joe, you need to stop sharing your screen and then unmute yourself. See if that works.
To say this was the problem I had, because the unmute button was underneath the tab that was on the screen, Joe. So there was a tab on the bottom that covered the microphone up.
If that doesn't work, I would just try and refresh your page if you can, please, Joe.
There's a question in the chat. Maybe we could go to that in the interim.
Yeah, that's a good idea. So Joe's going to talk about liquid cooling, and it's a technique for getting large volumes of heat away from IT racks, and liquid cooling can actually take the performance of racks up to maybe even 50 kilowatts a rack, which is way above what we would normally think about as a rack. Liquid cooling, it's being used in a lot of centers to improve efficiency in particular, and there are a number of data centers that are using it. Joe, are you back now?
Can you guys hear me now?
Oh, well done, mate.
Sorry for the initial technical issue. Let me share the screen again. I hope you guys can see the screen as well. Brilliant. Right. So I think that's thanks, Russell, for that. So, and sorry again for the technical thing. And after that power section, I think it's time to do a bit of the cooling down, or to cool down actually. So we'll go have a bit of introduction of the high density rack cooling solutions. So historically what's been the cooling solutions, and a bit of introduction towards liquid cooling as well, which Russell was actually giving an intro right now. So as a rough calculation of basically how the cooling's been distributed, so up to 3 to 10 kilowatts, we basically look into perimeter crack cooling solutions. And then when it comes to around 30 kilowatt of cooling, that's when we try to think about row-based cooling, which is having a cooling solution within the row, or basically even having it against a server, individual racks as such. Anything more than the 30 kilowatts, so let's say around 35 kilowatt or more than that, that's when we have to look into passive rear door cooling. And more than the 35, say around 50 kilowatt, and if there's a bit of a heat leakage or something like that, then that's when we look into active rear door cooling as well. Anything more than the 50, that's when liquid cooling comes into more precedence, and then the basic capex or the total cost of ownership or the return of investment becomes more of a sensible investment, liquid cooling, and there's more than 50 kilowatt of cooling coming in. We'll go through all these as a rough introduction sort of thing. So just to go through the initial or the historical way of cooling things, or which might be still be continuing in most of the applications as well. So traditionally, it was always used to be perimeter cooling solution, so where we'll have a perimeter or a crack unit sitting in one of the sides of the data hall, and then blowing air into the flow void, and the pressurized air comes out of the flow void through the grills, goes into servers. Servers gets cooled, hot air comes back into the crack units, and this gets recycled or cooled again, and circulation goes on and on. So that was a traditional system. To improve efficiencies, then there was the option of hot aisle containment coming in, or cold aisle containment, or the aisle containment as such. So this prevented any mixing of air as such. So which the advantage because of that being, we could raise the return air temperature that was coming into the crack units. That means that we could have same amount of cooling from a smaller footprint of units. The other option was with the containment, we could actually increase the water temperatures if it was a chill water cooling unit that we're looking into, which means that we could have a free cooling solutions coming in as well. So that's where the efficiency started bringing in. So from a traditional crack unit or crack cooling point of view, there are different options being looked into about how we could bring the efficiencies in, rather than just going into the traditional system as well. Now, go cracks again, as initially, which when Rob was giving you the slides, so Liebert was the one who, other companies who actually, Liebert is our company, which around 1965 were the inventors of the cracks unit systems, or the computer room air conditioning systems. Traditionally, cracks are DX units, and they have a differentiation which now we call any chill water perimeter cooling units as CRA units, or computer room air handling units as such. Now, traditionally, they have a DX system where the compressor, evaporator, condenser sitting outside, and then expansion valve. So that's a traditional refrigeration circuit as such. Now, to bring in more efficiency, there were different ways. So initially, it was not on the efficiency. Initially, it was a case of redundancies, where, like Russell was mentioning about N and N+1. So where do you get the redundancy? So that's where we have different options, where one of the options was to have a dual fluid unit coming in, or a dual circuit unit coming in. So you'll have a chill water coil, at the same time a DX coil. So in the case where the DX coil failure, you can have the chill water coil cooling the rooms with the chiller sitting outside. Then it came to the options of how to increase efficiencies, because the DX were bringing the PUEs quite high, or let's say the energy consumption is going really high. So then the option was to bring in free cooling in, and then that where the indirect free cooling option comes in, where again there are two cooling unit or cooling coils inside the unit, and there's a water cool condensers, and these water cool condensers in the ambient becomes okay. Then we can, these water cool condensers where the dry coolers are used, those dry coolers can act as a chill water cooling unit, and the chill water and the cold water goes into the system, into the rooms, basically into the cooling coils. So that's where the indirect free cooling coming in. To take one step further, then those where the ambience become again favorable, then we have the option of direct free cooling, which basically like the north of UK, we have more ambience less than 20 degrees throughout the year, or even close to 5 to 10 degree ambience in north of UK. We can have the direct fresh air coming into the rooms, where you don't have to run the DX compressors at all. The next stage that we could do was basically to have the highest amount of efficiencies, and at that time what we can do is what we have a system is called as a pump refrigerant economizer. Now you need to run a compressor when the temperature is really high, but if the temperatures are favorable external, we don't need a compressor to raise the refrigerant temperatures. We can just have a pump to have the mass flow in the system. So the compressors can be switched off, pumps can be turned on, and the condensers, external condensers, will become just like a free cooling condenser, or a free cooling refrigerant coil, let's put it that way. So that means that we get a highest amount of efficiency, because the highest power consumptions are the compressors, which are switched off, and we are running small pumps, which are minuscule when it comes to the amount of power consumption that we have. So as a rough estimate, we're seeing around 60% of efficiencies when you use this pump refrigerant economizer systems. Now, these were traditionally, like I said, we be seeing around a 70 to 80 kilowatt from a, actually 10 kilowatt from a racks point of view, but as a unit point of view, you can see up to 80 kilowatt. But then now there's been recently there have been discussions and studies about chill waters being used, or the amount of chill water units, or the amount of water that's being used in a data center or in a cooling room as such. And that's when the DX priority has come in again. So for that point of view, we've got the system, the pumped refrigerant economizer system extended to even bigger sizes, where even it's up to 400 kilowatts of capacities as well. And that means that we can avoid having, I mean, these 400 kilowatt systems can sit outside. It can take off the, I mean, we don't need a chill water as such. The whole unit gets cooled by the DX expansion systems as well. You can avoid any piping that is needed, additional refrigerants, and there's no refrigerant within the system. And there's always, it's a fully packaged DX system that you can get outside as well. And to increase the efficiency, we have the pumped economizer system on those units as well. So that's a traditional crack cooling, or the perimeter crack cooling. And the difference between the chill water system is that instead of the DX, you'll have a chill water coil in there, and the water is cooled outside by using a chiller. Now, moving on to the 30 kilowatt range, that's when we have the indoor cooling units. So the indoor systems will be sitting between the racks, and also you can have it against the servers as well. Now, this unit, the life was quite simple until we had the 30 kilowatt, and then now life is becoming really, or the world is becoming really, really complex, because there's more amount of security, there's high amount of data sources that's needed, data crunching that's happening, everything's becoming virtual, artificial intelligence, IoT, 5G, all these are coming in as well. And that means that the amount of computing that is needed is increasing, and everything has to be packed into a rack server as much as possible. So that's where the high amount of high density racks are coming in. So it's, I mean, the current pandemic is another reason as well. So because the healthcare sector has been having a huge amount of growth rate in the of computing as well. So because of this, we need to have, I mean, now users are looking into, or the data centers or even the server rooms are looking into high amount of density, more than 35 kilowatt, which is used to be the traditional limit as such. So it's not just in the healthcare sector, you can look into in the university side as well. So recently there's been a huge amount of uptake into the university, so you'll have more students coming in as well, and then there's more research coming in from the university side as well. So the computing power that is needed is going to get improved, is going to increase as well. So that means that we need to pack more server capacity, so more densities into the racks as well. Also, the technology from a CGU or a CPU and a GPU point of view as well, as you can see on that screen out there, the thermal density that's coming because of the amount of computing power is needed is increasing quite tremendously as well. From a dual core, we are even moving into 4-core, 8-core systems as well. And every time we increase the core for more computing, there's more thermal heat being generated. So all this thermal heat needs to be rejected somehow. And that's where the high density cooling solutions come in, and the different options that we can have is we can have a go for air cool, which will be the rear door cooling solutions. And then we can have a hybrid solution where there's a combination of the rear door cooling and also the air cool solutions and also liquid cooling. And then you can have a fully liquid cooling servers as well. So those are 3 different options that we can have currently for high density rack cooling solutions. Just to give a quick idea on passive rear door cooling, it's basically a chill water coil sitting right against a rack, and that can give you a cooling up to 35 kilowatt. It utilizes the fan power of the servers itself, so there's no additional fans or the additional input that's coming into the server rooms. So that means that the efficiency keeps increasing or you can keep the same efficiency as well, and then you get the amount of cooling that is needed as well. We'll have a chiller that is sitting outside, and these can be on a free cooling chiller as well. So that gives you the free cooling efficiency. So that means your PUE keeps increasing. There's no additional space needed as well. There's like a perimeter unit, and this can be connected to each and every rack. And because there's enough of capacity, or spare capacity on the passive cooling units, they can be working on an N+1 scenario as well. Some of the examples that we had, or some of the units that we already had, was like a telco unit, where a telco solution that we had, and there's video on demand and cloud services with our applications. And we've managed to incorporate the rear door cooling solutions into there, and that gives them the additional cooling that is needed, even because of the increased the computing, because the increased load that is shown on the servers basically. There's also a Green Cube GSI case study that we've done where the whole data center is running on rear door cooling. This is in Germany as well, showing a PU less than 1.1 on an annual basis. Moving on to the active rear door cooling. So this is basically a plugin that we can have. On the passive, just if there is a heat leakages within the servers, or if you need to get more capacity out of the passive rear door cooling, then you can have this additional fan modules fitted onto the passive to give you the active rear door cooling that brings your capacities up to 50 kilowatt as well. I understand I'm rushing through this because of the lack of time, but quickly moving into just to give you an introduction on the high density from when it comes to liquid cooling as well. And that's anything more than the 50, that's where you have to go into the liquid cooling side as well. There are different options from when it comes to liquid cooling. It can be a direct liquid cooling, where there's a chip cooling element in there. Then there's a hybrid option where the components are actually liquid cooled, or use, like, for example, a cooled fan, and then the fan just blows cold air into the servers. Then there are combined air and liquid cooling solutions where you can have a rear door cooling. At the same time, you can have the chip cooling as well. And there's a fully immersed or fully immersion cooling option as well. The immersion cooling option can be either fully contained inside the rack, or it can, or like the chip cooling, you can have a cooling distribution unit sitting outside. And this has a heat exchange system in there, a heat exchanger in there. So the facilities liquid and the external liquid is never mixed as such. The other advantage of having a cooling distribution unit is basically it maintains the temperature within the server rooms or in the facilities rooms at higher than the dew point of the dew point temperature. So that means that there's no condensation issues as well. So that's the different options of liquid cooling that we can have. So like I mentioned, of chip cooling and also immersion cooling as well. Both can be single phase or two phase. It depends on the amount of capacity that's needed as well. Just giving a high level classification for liquid cooling. So like we have the tier 1, tier 2, tier 5 classifications for, similarly, we have a W1 to W5 classification based on ASHRAE. So W5 being the most energy efficiency point of view, where you're running high water temperatures into the servers, which means that externally you can run it, or the heat rejection side can be used for heating local buildings as well. So you're basically reusing the heat as such. So you don't need a chiller or a dry cooler sitting outside. W4 is where the temperature is slightly lower, where instead of a chiller, now you're using a dry cooler. It is still efficient as well. But W1 to W3, you basically use a chiller external. So that means the amount of water temperature that's going into the server rooms is quite low. So if you're looking from a what kind of an operation that is needed, W5 will be the option if you want to reuse the heat as such. So coupled with the battery option, where you can where we can resell the heat back into the grid. Similarly, they have the option from the heating point of view, so where you can reuse the heat for local building heating as well. And finally, just a comparison between any cold plates and the immersion cooling, just to give you a rough idea as well. So usually the cold plate or the immersion cooling is best suited when the system heat is actually around 100 kilowatts of heat. From an immersion point of view, it is basically used where there's more than 100 kilowatts, so it gives you more and more heat rejection. But the thermal resistance on the immersion side is more than it's quite higher than compared to cold plate, because in the cold plate we use water or the ethylene glycol solution, but in the immersion it has to be a dielectric fluid. But because the application can reach more of the components, it means that it has to be it can have a high TDP components can be used it can be used to cool higher TDP components as well. Slightly on the development side, the cold plates cooling is, or the immersion, the chip cooling is slightly complicated, because you have to look into both air cooled and at the same time liquid cooling as well, because liquid cooling doesn't give immersion, or plate cooling doesn't give you 100% of cooling as such. It has to work directly onto a component. You're not immersing the rest of the components as well. So there's a bit of complication involved as well, and there needs to have enough space inside the rack to have both the rack and also the data room as well. From that point of view, the immersion becomes slightly advantageous because the entire system is getting cooled, but then comes the complexity of how you can service this, and also the type of components that can be used within immersion and liquid cooling as well, and chip cooling as well. So immersion has to have specific kind of components that can be immersed into the dielectric fluid, but on a chip cooling, all you have to have is a component or a plate that can be sitting on top of the GPUs or the CPUs as well. So there is advantages and disadvantages of cold plate and immersion. So it depends on the application that we are trying to use. We don't have to, I mean, I understand it's getting more and more, there are more data that is needed into our applications, or more data is getting processed, but whether we need to jump into that liquid cooling straight away is a question that we need to ask ourselves, whether are we catering to that future requirement? If so, then it'd be a good idea to think about liquid cooling. Otherwise, the option will be still you'll have the perimeter crack, the traditional crack, and the row cooling solutions, or what we can have is a hybrid solution where you can have the rear door cooling fitted right now, and then if needed be, you can have the chip cooling coming in as well. So these are different options that you can have, so nobody has to jump straight away and have the entire systems redesigned or entire halls redesigned to accommodate for liquid cooling as such. Now, if this is a discussion that we can have in detail, I understand I've been rushing through this because of the time limit, but which operation to go through, like Russell was mentioning, it's always a discussion that we can have in detail with a technical discussion as well, to go through whether it's a liquid cooling or perimeter cooling or indoor cooling that we need to have. Any questions as such? And that's basically from my end as well. If there are any questions, feel free to ask for the Q&A session.
Okay, somebody's got to bite the bullet. We've got 23 people who are listening, and somebody must have a question, surely. We've got Q&A in the end. Considering the value in exporting back to the grid, which Russell mentioned to meet grid demands response, has a simple payback on capital and costs being made? It's a very good question, but as you probably intimated, Richard, it's a very dynamic situation. So the answer is no. And there's a certain amount of future gazing required to enable that to happen. But Vertiv's point of view is that if you're planning something going forward with batteries in particular, then maybe it's something to build into a future design, and hopefully that would be okay. Do you share the PPT? Maybe Roxana can answer that question.
Russ, it might be worth mentioning that if you just review the replies, I've been responding in reply.
Oh, you have, yes. Yes, you have.
During the presentation.
So any other questions? Anybody else going to be putting their head above the parapet? Okay, well,
no problem. Okay, well, in that case, may I just thank everybody for attending. Absolutely, it's been a pleasure to pop back on, albeit to this particular remote opportunity to present. Hopefully, moving forward in the future, it'd be lovely to be able to attend in person as we have done previously, as opposed to doing it on this particular platform. But on behalf of Vertiv, I just thank everybody for their attendance. If there are any questions that come to light post-meeting, then by all means, you have our email addresses and contact details. Feel free to make contact, and we'll be more than happy to discuss opportunities or solutions or examples with you at some point in the future, should that be required. And on that note, can I say thank you very much for your time.
Thank you.
Thank you, guys.